Before the digital age, the story of data storage began with the most tangible of records: marks etched on cave walls, impressions carved into stone tablets, and the fibers of early paper painstakingly pressed and inked by hand. Though primitive by today's standards, these ancient methods laid the groundwork for humanity's enduring drive to capture, preserve, and retrieve information. As societies grew in complexity and scale, so did the need for more structured and reliable ways to manage collective memory. The Industrial Revolution marked a turning point, fostering systematic approaches to record-keeping that shaped the foundations of modern information management. What began as personal marks and communal records gradually became the backbone of governance, trade, and culture, with each generation building upon the methods of the last. The need to store information did not diminish over time. Instead, it intensified. Organizations and governments realized that without reliable ways to capture and protect their data, knowledge could be lost, legal compliance threatened, and opportunities for collaboration and effective decision-making reduced. The shift from paper to digital records did more than alleviate the burden of physical storage. It transformed the very nature of how information could be accessed, shared, and protected. Records once locked away in filing cabinets became available at the click of a button, and the accuracy, security, and efficiency of data management improved dramatically. Today, electronic records are deeply woven into the fabric of healthcare, business, and government, thanks to ongoing advances in cloud-based storage, artificial intelligence, and mobile accessibility. At the heart of this transformation lies a simple yet profound concept. Data storage is the collection and retention of information, whether for a fleeting moment or for generations. In the digital realm, this process is often compared to the workings of the human brain. Short-term memory, akin to random access memory, or RAM, provides immediate access to information needed in the moment. Long-term memory, by contrast, finds its counterpart in storage volumes. Devices and systems designed to retain data for the long haul, ensuring our digital assets are protected, retrievable, and safe from loss. The evolution of data storage devices mirrors humanity's relentless pursuit of better, faster, and more reliable ways to manage information. The journey from the earliest machine-readable forms of storage began in the 18th century with punch cards. First invented in 1725 for use in textile looms, punch cards became a revolutionary tool, not just for weaving patterns, but for encoding instructions and data in a form that machines could read. Charles Babbage, a pioneering figure in computing, envisioned their use in his analytical engine, and by 1890, Herman Hollerith harnessed punch cards to process the vast amounts of data collected in the United States Census. For decades, punch cards remained the primary means by which computers stored and processed information, their distinctive holes in stiff paper a familiar sight in offices and laboratories until the mid-1980s. As the demands of computation grew, so did the need for more efficient and flexible storage solutions. The transition from punch cards to magnetic storage marked a profound leap forward. In the late 1940s, the first forms of electronic memory began to appear. The Williams-Kilburn tube, developed in 1947, was the first high-speed electronic memory, storing data as electrically charged spots on the face of a cathode ray tube. Shortly thereafter, mercury delay line memory was introduced in 1949 with the EDSAC computer, storing bits as sound waves traveling through a column of mercury. These early forms of random access memory, or RAM, allowed computers to access information more rapidly and with greater flexibility than ever before. Yet the quest for reliability and scalability continued. By the 1950s, magnetic core memory emerged as the dominant technology, thanks to its durability and speed. Tiny magnetic rings threaded with wires could hold individual bits of information, enabling computers to store and retrieve data with remarkable efficiency for the time. In parallel, magnetic drum memory, first used in the Atlas computer in 1950, offered another means of electronic storage, with data inscribed on the surface of a rotating drum. The 1950s also witnessed the arrival of commercial tape storage devices, the UNIVAC. UNISERVO, introduced in 1951, became the first commercial tape drive, using reels of metallic tape to store large quantities of digital information. Tape storage was soon followed by the development of the first hard disk drive in 1956 when IBM unveiled the IBM 305. This device used stacked, spinning platters coated with magnetic material, with read and write heads poised above the surface to access stored data. The hard disk drive represented a milestone in storage technology, offering both speed and capacity that far surpassed earlier methods. From this point, the pace of innovation accelerated. The 1960s saw the introduction of cassette tapes for data storage, offering a compact and affordable way to back up and transfer information. Dynamic Random Access Memory, or DRAM, was developed in 1966, further enhancing the speed and capacity of computer memory. Floppy disks soon followed, giving individuals and organizations a portable, rewritable medium for storing programs and files. Each new technology built upon the successes and learned from the limitations of its predecessors. By the late 20th century, the progression of storage devices continued unabated. Magnetic tapes and disks, once the cutting edge, gradually gave way to optical storage media like compact disks and later to solid-state drives and flash drives. Each innovation was driven by the need for greater accessibility, scalability, and performance. File storage, block storage, and object storage became prevalent forms, each suited to different types of data and usage scenarios. The significance of these advancements cannot be overstated. Efficient storage systems not only protect information from loss, they also enable organizations to comply with legal requirements, enhance collaboration by making information readily accessible, and support the strategic decision-making that drives business success. Digital storage, in particular, has reduced the need for physical space, making it possible to manage vast quantities of data on devices no larger than a book, or even on remote servers accessed through the cloud. Despite the remarkable progress witnessed over centuries, the fundamental purpose of data storage remains unchanged: to preserve information for the present and the future. Whether it is the enduring marks on a cave wall, the click and whir of a punch card machine, or the silent operation of a modern solid-state drive, each method has served as a bridge between memory and possibility. Today's digital world rests on the achievements of countless innovators who reimagined how we capture, store, and retrieve the essence of human knowledge. As we look back across this timeline from stone and paper to magnetic and digital media, we see a story of adaptation and ingenuity. The devices themselves have changed, but the underlying need to safeguard and access information continues to shape how we live, work, and connect. The journey of data storage is far from over, but its foundations are deeply rooted in the history of human civilization and in the enduring quest to remember, to share, and to build upon what has come before. When you think about the devices that quietly safeguard your digital photos, work documents, and favorite songs, you are entering the ever-evolving world of data storage. At its heart, this landscape is defined by three main types of secondary storage devices: magnetic, optical, and solid-state. Each represents a unique solution to the challenge of preserving data reliably, drawing on distinct scientific principles, developing along its own historical path, and finding particular roles in our personal and professional lives. Let us start with magnetic storage, the oldest and, for much of computing history, the most widely used method of data storage. Magnetic devices operate on a principle that is both elegant and robust. They use magnetized regions on a surface to represent binary data. In practice, information is encoded by altering the polarity of tiny sections, often on spinning disks or long strips of tape. This technique underpins familiar devices like hard disk drives and magnetic tapes. Hard disk drives, for instance, store data on rapidly rotating platters coated with a material that can be magnetized in tiny, distinct areas. Read and write heads hover just above the surface, flipping those regions as needed to record or retrieve information. Magnetic tapes, on the other hand, store data sequentially along thin reels, making them especially well-suited for backing up large volumes of information over the long term. Why has magnetic storage remained so popular? Its appeal lies in affordability and capacity. Magnetic tape storage, in particular, is known for its reliability, low cost, and impressive longevity, often exceeding 30 years under proper conditions. It boasts low error rates and can store massive amounts of data at a fraction of the price of other technologies. This is why, even as newer forms of storage have emerged, organizations continue to use magnetic tape for archival and backup purposes. However, magnetic storage does have its limitations. It is relatively slow, especially when accessing specific pieces of information. Tapes require sequential access, meaning you may have to wind through large sections to reach the data you want. Hard disk drives, while faster and more flexible, are still limited by the need to physically move parts. They are also vulnerable to damage if dropped or exposed to strong shocks, a weakness that contrasts sharply with the more rugged designs of later storage technologies. The rise of optical storage in the late 20th century brought a dramatic shift in how consumers and businesses approach data. Optical devices like compact discs, digital versatile discs, and Blu-ray discs introduced a novel way to read and write data with light. Lasers are used to burn microscopic pits and lands into a disk's data layer. When a laser beam is later aimed at the surface, it measures differences in reflectivity to distinguish between the pits and the flat areas, translating these patterns into digital information. This method is not only precise, it also allows for high-density storage on a compact, portable medium. Optical storage devices gain popularity largely because of their durability, low cost, and ease of use. Unlike magnetic disks, optical media are immune to magnetic fields, making them a stable choice for long-term storage. The emergence of optical disks in the 1990s provided consumers and organizations with a cost-effective way to store and share photos, music, movies, and software. Compact discs became the standard for distributing music albums and software packages, while digital versatile discs and Blu-ray discs offered even greater capacities for movies and archival data. These devices also proved resilient in daily use. Their lack of moving parts within the disc itself, combined with the inherent stability of the materials, meant that data could be preserved reliably over years. However, optical storage comes with its own set of trade-offs. While the discs themselves are portable and simple to use, they are less convenient for rewriting or frequently updating data. For the most part, traditional compact discs and digital versatile discs are either read-only or allow only a limited number of rewrites. Access speeds are also slower compared to more modern alternatives, and the physical nature of the discs means they can be scratched or damaged if handled carelessly. Over time, the widespread adoption of cloud-based services and high-capacity solid-state storage has further reduced the everyday role of optical media, though they remain a favored option for certain archival and distribution tasks. The most recent revolution in data storage technology is solid-state storage. These devices take a fundamentally different approach. Instead of relying on moving parts or changes in magnetic fields, they store data electronically in non-volatile memory chips. Solid-state drives, universal serial bus flash drives, and secured digital cards all belong to this family. At the heart of solid-state storage is flash memory, specifically NAND. Flash, which organizes data in arrays of memory cells capable of holding electrical charges over long periods, even when the device is powered off. What sets solid-state storage apart is its speed and resilience. With no moving parts, solid-state drives can access data almost instantaneously, vastly outperforming traditional hard drives in both read and write operations. This makes them ideal for applications where speed is critical, such as booting operating systems, loading large files, or running demanding applications. Furthermore, solid-state devices are more resistant to physical shocks, making them well-suited for portable devices like laptops, tablets, and smartphones. The internal workings of solid-state drives are managed by sophisticated controllers that handle data allocation, error correction, and wear leveling, a technique that distributes data evenly across the memory cells to extend the device's lifespan, NAN. Flash comes in several varieties, each offering a different balance of reliability, capacity, and cost. Single-level cell flash is the most robust and expensive, while multi-level cell, triple-level cell, and quad-level cell variants provide progressively higher capacities at the expense of endurance. Despite their many advantages, solid-state devices are not without drawbacks. They are more expensive per gigabyte compared to magnetic or optical media, and their lifespan, while generally sufficient for typical use, is limited by the number of write and erase cycles each memory cell can endure. Over time, this can lead to degradation, especially in devices that experience heavy write activity. Nonetheless, the combination of speed, durability, and energy efficiency has made solid-state storage the technology of choice for modern consumer electronics and enterprise systems alike. Comparing these three categories, magnetic, optical, and solid-state, highlights the trade-offs inherent in any storage solution. Magnetic devices continue to offer unmatched value for large-scale, long-term storage, particularly in archival settings where cost and capacity matter more than speed. Optical media, while less prominent today, remain valued for their stability, simplicity, and immunity to magnetic interference, making them a dependable choice for archiving and distribution. Solid-state devices, with their lightning-fast performance and resilience, are rapidly becoming the default option for everyday computing needs, even as their higher price and finite lifespan remain important considerations. The evolution from magnetic to optical to solid-state storage reflects not just technological ingenuity, but an ongoing dialogue between the demands of users and the possibilities of science. Each technology, in its time, has pushed the boundaries of what is possible, offering new ways to safeguard, access, and share the information that powers our world. As data volumes continue to soar and our reliance on digital tools deepens, the search for better, faster, and more reliable storage will undoubtedly continue, building on the foundation laid by these remarkable devices. Picture for a moment the invisible world inside your computer or phone, the humming, whirring, and blinking that signal the ceaseless flow of ones and zeros. Behind every song you stream, every photograph you snap, and every document you save, marvels of engineering work tirelessly to manage and protect your data. Modern storage technologies are more than just repositories for digital memories. They are intricate systems designed for speed, reliability, and capacity, all operating quietly in the background of our digital lives. Let us begin with the hard disk drive, or HDD, a cornerstone of secondary storage for decades. At its core, a hard disk drive is a symphony of precision mechanics and magnetic wizardry. Inside, metal platters coated with a special magnetic material spin at thousands of revolutions per minute. Hovering just fractions of a millimeter above these platters are the read and write heads, attached to delicate actuator arms. These heads never physically touch the platters. Instead, they float on a thin cushion of air generated by the spinning disks. When your device writes data, the head changes the magnetic orientation of tiny spots on the platter's surface, encoding each bit as either a north or south magnetic field. Reading works in reverse. The head senses the magnetic orientation and translates it back into digital information. Modern hard drives are astonishing in their capacity. A single platter can store over 1 trillion bits of information, an almost inconceivable density considering each bit is represented by a minuscule patch of magnetic material. The platters are stacked and spun in unison, with each surface adding to the total capacity. The result is a device capable of holding immense libraries of information, all at a relatively low cost per byte. Yet, this mechanical ballet comes with trade-offs. Every data request requires the drive's actuator arm to dart across the platter, aligning the head with the correct track before reading or writing can begin. This physical movement, though swift, introduces latency, an unavoidable pause while parts move into position. As a result, hard disk drives are often slower than their solid-state counterparts, especially for random data access. Nevertheless, the balance of capacity, affordability, and mature manufacturing ensures that hard disk drives remain popular in personal computers, enterprise servers, and archival systems where vast storage is essential. In contrast to the spinning world of hard disk drives, solid-state drives, or SSDs, operate in near silence and at remarkable speed. The key lies in flash memory, specifically NAND flash, a technology that stores data as electrical charges in microscopic cells carved into silicon chips. Unlike magnetic storage, there are no moving parts. Instead, a series of complex controllers orchestrates the flow of information, managing where each bit is stored, how it is retrieved, and how the physical memory cells are maintained over time. A solid-state drive's controller is its unsung hero, responsible for a suite of critical tasks. Where leveling is perhaps the most vital, it ensures that write and erase cycles are evenly distributed across all memory cells, preventing premature wear out of any single area. Garbage collection, another essential function, reclaims space from previously deleted files, consolidating free blocks to maintain efficiency. The TRIM command, supported by modern operating systems, helps the solid-state drive identify which blocks of data are no longer needed, further optimizing performance and extending the drive's useful life. All these processes happen automatically, unseen by the user, but they are crucial to the solid-state drive's reputation for speed and reliability. The benefits of flash storage are clear in everyday use. Solid-state drives offer high-speed access with low latency, making them ideal for tasks that demand quick file transfers or rapid application launches. They come in a variety of form factors, from the familiar 2.5-inch drives to compact M2 sticks and large enterprise-grade modules. In both consumer laptops and the data centers powering the digital economy, solid-state drives have become indispensable for workloads where speed is paramount. Yet, even as they excel in performance, solid-state drives are not without limits. The endurance of flash memory is finite, defined by the total number of write and erase cycles each cell can survive. Sophisticated controller algorithms help mitigate this by distributing writes and managing wear, but heavy usage can eventually degrade the device. Despite this, the combination of speed, durability, and falling prices continues to expand the reach of solid-state technology. But what happens when the demand for storage exceeds the bounds of local devices? Enter cloud storage, a technological leap that has redefined how individuals and organizations manage their data. Rather than storing files solely on a local drive, users can now upload digital information to remote servers managed by third-party providers. These off-site servers are not isolated machines. They are part of vast, distributed architectures where data is broken into pieces and copied across multiple locations. This distributed approach brings remarkable advantages. First and foremost is scalability. Cloud storage can grow or shrink on demand, accommodating the unpredictable ebb and flow of data created by users around the globe. For businesses, this means avoiding the expense and complexity of building and maintaining their own data centers. Instead, they can tap into the infrastructure provided by industry giants like Amazon Web Services, Microsoft Azure, or Google Cloud, choosing from public, private, or hybrid models depending on their needs for security and control. Reliability is another hallmark of cloud storage. By distributing data across multiple servers, often in geographically distinct regions, providers can ensure that a hardware failure or natural disaster in one location does not lead to data loss. Redundancy is built into the system. Copies of your files exist in several places, ready to be retrieved if needed. This is particularly vital for backup, disaster recovery, and the management of centralized data lakes that serve as repositories for vast and ever-growing pools of information. Security, of course, is always a concern when personal or sensitive data leaves your direct control. Cloud storage providers employ a range of safeguards to address these worries. Encryption protects data both at rest and in transit, while authentication and access controls determine who can view or modify files. Regular backups and audits add further layers of protection, giving users and organizations confidence that their digital assets are both safe and accessible. The impact of cloud storage goes beyond convenience and security. It is transforming the economics of data management. The elastic capacity of cloud solutions means that organizations pay only for what they use, avoiding the cost of unused infrastructure. For small businesses, this levels the playing field, enabling them to access world-class storage and backup services once reserved for large enterprises. For larger organizations, the ability to manage colossal volumes of unstructured data, documents, images, videos, sensor data is now a driving force behind digital transformation. As global data creation accelerates, the importance of these modern storage technologies only grows. Experts project that, by 2025, the world will generate an astonishing 180 zettabytes of data, a volume that makes the quest for reliable, scalable, and efficient storage even more urgent. In response, enterprises are increasingly adopting hybrid storage models that combine the advantages of on-premises solutions control and low latency with the flexibility and cost savings of the cloud. Whether spinning at the heart of a server, silently storing memories on a sleek solid-state drive, or floating in the digital ether of the cloud, today's storage technologies are the unsung foundation of modern life. They manage our precious information with a blend of mechanical precision, electronic ingenuity, and networked resilience. Though invisible to most, their impact is everywhere, shaping the speed, security, and scale at which we live, work, and create in the digital age. Choosing the right data storage device can feel like standing at a crossroads, each path offering its own set of trade-offs and opportunities. In today's world, both organizations and individuals must weigh a complex blend of factors: speed, capacity, durability, security, and, of course, cost. The decision is rarely straightforward. It depends not only on how much data needs to be stored, but also on the types of data, how often it will be accessed, and long-term goals for growth and innovation. At the core of these choices lies a fundamental truth: not all storage devices are created equal. Solid-state drives, for example, are valued for their speed and responsiveness, making them ideal for tasks that require quick data retrieval and frequent access. Hard disk drives, while slower, offer a balance between capacity and affordability, serving as reliable workhorses for many applications. Magnetic tapes, though the slowest in terms of access, excel at backup and archival purposes, storing large amounts of data at a lower cost per byte. Each option has its own strengths and weaknesses, and the key is to match those characteristics to the specific needs of the task at hand. Beyond raw performance, durability and reliability are crucial considerations. A storage device might offer impressive speed or capacity, but if it is prone to failure, the risks can quickly outweigh the benefits. When evaluating hard drives, it is important to look beyond upfront cost or advertised capacity and consider design, compatibility, and especially expected lifespan. Security-focused hard drives are engineered for continuous operation, built to withstand constant use and deliver dependable performance over time. Devices from reputable brands, especially those based on proven, slightly older models, are often safer choices than the latest, untested innovations. While the appeal of cutting-edge technology is strong, stability and a proven track record of reliability tend to offer greater value when data integrity is at stake. The concept of mean time between failure, or MTBF, is a useful metric for estimating the expected longevity of hard drives and other storage hardware. Yet no device lasts forever. Regular testing and monitoring are essential to catch early signs of wear or impending failure. Disks, for instance, should be periodically checked for physical damage, such as scratches or signs of delamination, and data should be migrated off aging media every 2 to 5 years to avoid unpleasant surprises. Redundancy is a core strategy when adopting any new storage device. Keeping duplicate copies ensures that if something goes wrong, recovery is swift and straightforward. But reliability is only part of the equation. The way data is backed up and protected can mean the difference between a minor inconvenience and a catastrophic loss. Identifying which data is truly critical is the first step. Not all files are created equal, and some are far more essential to ongoing operations or personal history than others. Once the important data is identified, the choice of backup strategy comes into play. There are several established approaches. Full backups create complete copies of all selected data. Incremental backups capture only the changes since the last backup. Differential backups gather all changes since the last full backup. And more specialized methods, such as image-based or file-based backups, offer additional options. Each method has its own advantages in terms of speed, storage requirements, and ease of restoration. Regardless of the approach, the key is to ensure that backups are not only created, but also regularly tested for restorability. A backup that cannot be restored in a crisis is, in effect, no backup at all. The most robust backup strategies are comprehensive and layered, including plans for backup frequency, how often data is saved, and retention, how long each backup is kept. The physical or virtual location of backups is also crucial. Storing all copies in one place exposes them to the same risks, whether fire, theft, or disaster. Automation helps maintain discipline, ensuring that backups occur on schedule, while physical copies and cloud or snapshot backups add further resilience. Disaster recovery planning brings all these elements together, outlining clear procedures for restoring data and minimizing downtime. Security, naturally, remains a central concern. Encrypting data both at rest and in transit is essential for protecting sensitive information. The rise of technologies such as blockchain offers promising new ways to verify the authenticity and integrity of stored data, especially in environments where trust and traceability are critical. Object storage has emerged as a scalable and redundant solution, particularly well-suited for managing vast, unstructured datasets in a flexible, cost-efficient manner. Data tiering and the use of cold storage, where infrequently accessed data is moved to less expensive, slower media, further optimize costs without sacrificing long-term accessibility. For organizations seeking to future-proof their data storage, the challenge is not simply to find a solution that works today, but to build an architecture that can evolve as needs change. This involves integrating a mix of sources, cloud, software as a service platforms, and on-premises systems, while avoiding dependence on a single vendor. Automation, agility, and resilience are essential, as is the need for clear and thorough documentation and policies. As new regulatory requirements emerge and the volume of data continues to grow, automating compliance through artificial intelligence can help organizations remain nimble, efficient, and secure. Small and medium-sized businesses in particular benefit from flexible storage strategies that combine on-premises devices with cloud and data center resources. This hybrid approach delivers scalability and security without requiring large upfront investments. Data centers, for example, offer on-demand resources that can expand as a business grows, and their robust disaster recovery capabilities help ensure continuity even in the face of unexpected setbacks. Centralizing data storage and management is another pillar of sound practice. By consolidating disparate data sources and streamlining storage environments, organizations can maximize accessibility, security, and operational efficiency. Software-defined storage solutions unify management across different hardware and platforms, giving administrators greater control and flexibility. At the same time, optimizing storage tiers, matching the cost and performance of each device to the importance and access patterns of the data, prevents overspending while preserving performance where it matters most. On the individual and small team level, strong file naming conventions and consistent metadata management make it much easier to locate and organize information. The 3-2-1 backup rule, 3 copies of data stored on 2 different types of media, with at least 1 copy off-site, remains a standard for robust data protection. Separating backups from simple file synchronization, using version backups, and regularly testing restore processes all contribute to a system that stands up under real-world pressures. As storage devices age, proactive maintenance becomes vital. Hardware upgrades, periodic data migrations, and vigilant monitoring for early warning signs can prevent small issues from becoming major crises. Environmental factors, such as temperature, humidity, and dust, also affect the longevity and reliability of storage hardware. Cost optimization is achieved not only by selecting the right device for each job, but also by tuning backup schedules, retention policies, and storage allocation to match actual usage patterns. Ultimately, the successful selection and management of data storage devices is less about finding a one-size-fits-all answer and more about building a framework that adapts to changing needs, stands the test of time, and safeguards the information that matters most. The science of data storage, for all its technical complexity, is ultimately about trust that memories, records, and knowledge will remain accessible, secure, and intact no matter what the future brings.